Hello dear friends, a great welcome to this series on engineering mechanics. Myself Jarajan P. This is class 8 of the series and it covers only one topic, that is solved examples related to the computation of moment of a force about a point in vector format. So let us start our class. So we will start with example 1. So let me first read the problem. Two forces act on the road as shown in the figure A. Determine the resultant moment they create about the flange at O. Express the result as a Cartesian vector. So this is the first problem which demonstrates how to make the computation of the moment of a force about a point in vector format. So let me explain this example 1. The sketch is given in figure A. So as you can see that this is a bent rod, okay, and the bent rod has got three segments. So that's the OA is one segment and it has got another segment, and we are given 3 points OAB. The coordinates are clearly defined here, and as you can see that this bent rod, okay, is connected to a wall using a flange arrangement. So don't worry about what the flange arrangement, it is a connection component. So we are asked to find out what will be the turning effect produced by F1 and F2 combined about the point O, or we need to compute the moment of the forces F1 and F2 about the point O. Now here one more thing I would like to tell you is the force F1 and F2, they are already given in the vectorial format or the Cartesian format. So we can straight away use them in our computations. And another thing is that for the computation of the moment of the force F1, right, we require a position vector which is directed from point A to any point on the line of action of the force F1. Now here A, as shown in the sketch, A is already a point on the line of action of F1. So we can directly use OA as the position vector for the computation of the moment produced by F1. Similarly, for F2, first of all we need to find out the position vector of any point on the line of action of the force F2 about the point O. Means we can use in this case a position vector drawn from point O to point B, okay, as my RB for the computation of the moment produced by F2. So let us proceed for the calculations. So as usual, so please remember one very important thing: the moment of a force about a point is computed using the simple expression m equal to r cross f, and here r indicates the position vector which is drawn from the point about which the moment is to be calculated to any point on the line of action of the force. So let us use RA as a position vector for the computation of the moment produced by F1. Now, what's the coordinate of A? Obviously, from this, it is important to note the coordinate very clearly and carefully. And we know that A is a point on the y-axis, and its coordinate is A050. Correspondingly, the associated position vector RA is nothing but it's the 5j feet. So please note down the units also very clearly. Okay. And now for the moment produced by F2, let us use RB as the corresponding position vector. So we note down from this figure A that the coordinate of B is a 4, 5, minus 2, and accordingly the corresponding position vector is 4i plus 5j minus 2k. So therefore, we can go for the computation of the resultant moment produced by F1 and F2 about the point O using the simple expression which was already discussed earlier as vector MRO is equal to sigma r plus F. Very specifically in this case, this will turn out to be vector RA cross vector F1 plus vector RB cross F2. The first term indicates the moment produced by F1 about O, and the second term indicates the moment produced by F2 about the point O. So as per our earlier discussions, each of this term can be put in the determinant format. So we'll write down a determinant for the first term ijk, and the second row will be the coefficients for the RA. RA, we know that it has got only j component, so it can be written as 0, 5, 0, and then F1. F1 is already given in the problem as minus 68 plus 40j plus 20k. It does mean that the third row will contain minus 60, 40, and 20 plus. And the second term can be represented by another determinant which can be written as determinant ijk, and the second term will be the corresponding position vector which we know that it is 4, 5 and minus 2, and the force F2 is already given 80I plus 40J minus 30K. So just enter these coefficients here, and on expanding this determinant and doing the calculation, we find that the resultant moment is 30I minus 40J plus 60K. Now please remember one very important thing. Here we expressed the resultant moment about the point O in the Cartesian format. Now suppose that you are interested in marking this moment MRO as in the vector format in the sketch. How do you do it? So look here, for example, this resultant moment MRO, it is marked in the sketch. So now you may ask me, sir, how do we know that it is directed this way only? It's very simple. So first of all, if you want to mark the moment of the force about the point as a vector as shown in this figure, number one, you need to know its magnitude. So this magnitude you can directly obtain because you know that it is the square root of 30 square plus 40 square plus 60 square. Okay, so all those calculations are not repeated here. And one very important thing is that how do we know that it is directed in this way only? So this is done simply by the calculation of the so-called direction angles. That means for this vector, you can directly obtain the direction cosines. How do you obtain the direction cosines? You can calculate the unit vector along vector MRO. And from these coefficients, you can calculate the angles alpha, beta, and gamma. And those calculations are not repeated here. And for this specific MRO, which is obtained as 30I minus 40J plus 60K, you can obtain alpha beta value as alpha is equal to 67.4, beta is equal to 121 degrees, and gamma equal to 39.8 degrees. And if you respect these angles, you will find that there is only one position for this moment vector MRO as shown in the figure. Now again, you may ask me a question whether this produces a clockwise moment or an anti-clockwise moment about the point O, because this will not tell you whether it's a clockwise or an anti-clockwise moment. And from this vectorial format, it is very simple again. What you need to do is you just point your thumb of the right hand in this particular direction. Obviously, you know that in order to have your thumb directed in this direction, you have to fold the fingers of your right hand in the anti-clockwise direction, indicating that this moment vector MRO, it produces an anti-clockwise or a counterclockwise turning effect about the point O. So this is all about example number 1. Now let me take you to another example. Please remember that the purpose of the example is to make the concept very much clear, okay, and not to make a very exhaustive calculation. Okay. Now example 2 is good enough to give some kind of an eye-opener into the calculation of the moment of a force, both using the scalar as well as a vector format, and make a direct comparison. So let me read the problem statement. Example 2. A force vector F, it acts at the end of an angled bracket as shown in the figure. Determine the moment of the force about the point O. Look here. This is the problem sketch. So here we have got a bracket which has got obviously the shape of a triangle, and as you can see that this bracket, it is fixed to a vertical wall, and the end of the bracket, it is subject to an inclined load F equal to 400 Newton, and as shown in the sketch, it is inclined at an angle of 30 degree with the vertical, and the geometry of the bracket is clearly identified so that we can compute the desired position vectors as and when we go for the computation of the moment of the force in the vectorial format. So as this is a simple two-dimensional problem, it is better that we consider both opportunities. We can start obtaining the solution both in the scalar format and vector format, so that increases our confidence. So let us solve this problem first in the scalar format. So in order to solve this problem in the scalar format, what we'll do is, in order to make our calculations very simple, look here, you know that in the scalar format, magnitude is obtained as F into D, where D is the perpendicular distance measured from the point where the moment is to be calculated to the line of action of the force F. Now you know that the force F is inclined. So we may have to do some trigonometric calculations, okay, in order to find out the perpendicular distance of the line of action of F from the point O. Instead, we can make our calculations much more simpler by resolving the force F into two components. That is, one a horizontal component and the other one is a vertical component. So this is what is written here. So the force F is first resolved into the x and y components. Now from this angle, it is easy for us to find out the horizontal component of F 400 Newton is 400 sin 30 and the vertical component is 400 cos 30. Now you will find that the computation of the moment arm is very simple because we have replaced this inclined force by a horizontal and a vertical component. So as seen from this sketch, the moment calculations are carried out as, so before that we consider all the counterclockwise moments as positive. Now let us go for the calculation of the moment about the point O. So considering the horizontal force, we know that this horizontal force of 400 sin 30, it produces a counterclockwise moment about the point O. So it is a positive moment. So it is 400 sin 30 into, what's the lever arm? That's the perpendicular distance of the line of action of this force from the point O, that is point 2. Now coming to 400 cos 30, it produces a clockwise moment about the point O, right? So accordingly, this will be recorded as minus 400 cos 30 into, what's the lever arm in this case from the point O is 0.4 meters. So it is minus 98.6 Newton meter. What does this indicate? We assumed the counterclockwise moment as positive and obtained a resultant magnitude of the resultant moment at the point O as minus. It means that the resultant moment that is acting at the point O is in the clockwise direction. Okay, clockwise direction. So we obtained the magnitude 98.6 Newton meter, and we also know that it acts in the clockwise direction at the point O. Now let us solve the same problem in the vector approach. So obviously in the vector approach, first of all we need to conveniently define the position vector that is directed from the point O to any point on the line of action of the force F. Now in the problem it is already given the coordinate of one point on the line of action of the force, which can be conveniently used in the definition of the position vector. Now we know that this point has got a coordinate of, what's x coordinate? It is 0.4 meters. And what's the y coordinate? Remember that this is your positive y axis. It does mean that the y coordinate associated with this point will be minus 0.2. It does mean that the position vector r, which is obtained from the by drawing a vector from the point O to any point on the line of action of the force F, will be vector r, which is 0.4i minus 0.2j meters. And from the non-components, horizontal as well as the vertical components, we can express vector F in the Cartesian format as fxi plus fyj. What is fxi? Horizontal component, that is 400 sin 30i. And we know that our vertical component, it is directed in the negative y-axis. So it does mean that we have to use minus 400 cos 30j. Okay, so this can be written as 200i minus 346.4j. So let us calculate as usual the moment of the force about the point O as vector r plus vector F, as put it in a determinant format ijk, and the second row will be the coefficients of r, which is 0.4, 0.2 and 0, and we have the force F, that is 200 minus 346.4 and 0. So on simplifying these calculations, we obtain the resultant moment about the point O in the vectorial format as minus 98.6 kilonewton meter. Now look into this expression. We find that the magnitude of this moment is 98.6 Newton meter, which matches exactly with our value obtained in the scalar approach. Now regarding the direction, remember that it is directed along the negative z-axis. Obviously, look here in this particular sketch, it is understood that if somebody asks you what is the direction of the positive z-axis, simply use your right hand rule. Curl the fingers from x to y. Okay, so you will find that z-axis, it is directed away from the page, through O, away from the page. Okay, so it does mean in this case it is minus, means that it is directed into the page. Directed into the page means that it is having a clockwise moment. So and this direction matches with the one which we obtained in the scalar format. Thus we find that the magnitude and direction of the moment that is computed at the point O using both the scalar as well as the vector approaches matches well. Okay, so that is all about this class. So we will start the next class with the other topic. Till then, have a nice day.